Okay, today we are talking about fields. And because we have these two analogous equations with each other, gravitation, universal law of gravitation and Coulomb's law, okay, they have a similar uh, uh, structure when it comes to they create fields. Essentially, it's a force field that they create. All right, so I do want to start with gravitation, where we know that the force of gravity equals G m1 m2 over r squared, and it's negative and r hat, meaning it's in the radial direction. Then we have the force of electricity, which equals k q1 q2 over r squared, and this is also r hat because it happens in the direction of the other force. Now, I want to set our Wayback Machine of lecture back about 600 years, 400 years. When Newton discovered two things. Okay, that if we have a ball that we are dropping close to the planet and an elephant that we are dropping close to the planet, okay, both of these are going to accelerate at the same rate. Now, the force of gravity on the ball and the force of gravity on the elephant, okay, the force of gravity on the elephant is going to be much larger than the force of gravity on the ball because the elephant's bigger. The elephant has more mass, therefore we're going to have more force on the elephant. However, for both of them, the force equals mass times acceleration, and this acceleration equals g. Right? So the acceleration, or the value of force divided by the mass for both of them, is equal to our acceleration. Does this idea change if we move the ball and the elephant further away from the surface of the Earth? Okay, the idea that they will accelerate, that they will have the same acceleration, shouldn't change. The value of the acceleration will change. The force acting on these things will change. But if we recognize that this force of gravity equals mass times acceleration, and that's really just equal to this thing over here, mass times acceleration equals G m1 m2, and we'll call this m2 over r squared. All right, if this is the value of our gravitational force, and this is the value of our gravitational force, we've just simplified it for this a acceleration near the Earth, that we can cancel the mass of the object that's falling. And so the acceleration due to gravity is equal to g times the mass of the Earth over the distance from the center of the Earth squared. You guys follow me here? Question? I just assigned m1 to be the Earth. Here, wait, that's a good question. I can mass of the Earth, mass of the ball, mass of the ball, right? So we cancel out the mass of the ball. We're left with g times mass of the Earth over r squared. This concept right here is telling us that the acceleration due to gravity varies with the distance, but it only varies with the distance from the Earth. The mass of the Earth is the same. So, right, if we create our big blue dot, which is the mass of the Earth, and we pick some point in space, what is the direction of our acceleration? It should be the same as the direction of the force, right? Which would be towards the center of the Earth. Based on the assignment you guys did yesterday, how would this change if I move this closer to the Earth? What would happen to the length of this arrow? It would increase, right? It would get longer the closer we get. It would decrease the further away, right? So let's say this point is here, and let's draw another one that's further away, but it's out here, right? This arrow would be shorter, right? Okay, and if we have them right next to the Earth, it's going to be quite a bit longer, yeah? What we have here, or what we are finding here, is no matter where we are around the planet, we can draw an arrow that would represent our acceleration towards the center of the planet all the way around. Okay, those arrows that we find, okay, are called a field. Okay, and the idea of the field is it is the collection of all of the acceleration vectors towards the center of the planet. Okay, so close your eyes for a second and envision all of the arrows, no matter where you are around the planet. Imagine all of the arrows that would be pointed towards the planet just based on where you are around the planet. What would it look like? Okay. It would look like a whole bunch of arrows pointed right at the center of the planet, right? It'll be everything pointed in. Okay, that is called our gravitational field. Okay, that is our gravitational field. And in essence, it is the collection of all of the acceleration vectors within the gravitational influence of the Earth. But as we get close to the Earth, they all point to the center of the Earth. So we're going to zoom in on this really, really close. Gravitational field look like? If we're flat, it looks straight down, which is consistent with what Galileo and Newton discovered when we discovered gravity, that all objects accelerate to the Earth at the same rate. That no matter where, if you're close to the Earth, that acceleration vector is going to be equal for all massive objects near the Earth. All right, so if you're close to the Earth, it's going to look like this. But if you're further away from the Earth, this is the same as a zoomed out view of what the acceleration is going to be further away from the center of the planet. Okay, well, actually, there are some rules for this when you guys draw a gravitational field. One, the field lines, I don't want to say are parallel, okay? That our field lines never cross each other, and the number, okay, and I'll read this because I know my handwriting is terrible, that the number of lines that you draw is proportional to the field producing property. So just as gravity looks like this, what is the field producing property? What produces gravity? Well, Earth, but what about the Earth? What property of the Earth produces the gravity? The mass of the Earth, right? Okay, that's the me, right? That's a constant. This changes its value, but it's the property of the mass of the Earth that's causing the that causes the gravity. Mass causes gravity. Okay. So in Coulomb's law, way back up here, what is the field producing property? Instead of mass, it is our charge on one of the particles. So we're going to extend this idea to electric field. Okay, so our electric field is the same idea. Okay, so we know that we have two charges. Okay, and for our purposes here, we're going to call this they're both going to be positive charges. All right, so this is going to be Q1, which is positive, and this is going to be Q2, which is also positive. Okay, first of all, what is going to be the direction of the field on Q2? All right, let me rephrase that. If we are holding Q1 steady, what is the force on Q2? Or what direction? What's that? Towards Q1, if they're both positive? They're both positive. So it'll be away, right? Like charges repel, right? So this is going to be, okay, so it's going to be that direction. What would happen to this line if I make it, if I move Q2 shorter, closer? If I move this closer, what happens to our line? Okay, it should get longer, right? The force should be greater because the objects are closer together. Yeah? Same rules apply. It's the same thing as gravity. The force is going to be greater the closer the two elements are. But does it matter. Okay, so here's our force for our electrical force. Up here we had our gravitational force. We got this by determining our force divided by our force producing property of the other thing. Yeah? So we're going to do the same thing down here, and we're going to find our force divided by our force producing property is going to give us kq1 over r squared. This is our field. It's our electric field, our field strength of q1. E? Yes, this stands for electric field. This equals Fe over Q2. If I divide by Q2, if I divide by this other charge, okay, then we'll get this, right? So if I divide Q2 over here, Fe over Q2, this is essentially the same thing as the acceleration of our gravitational thing, right? But this doesn't quite count as graduation. This is our force per unit charge. This is our force per coulomb equals this. But the idea is the same, that if these are all positive charges, that no matter where I put no matter where I put a charge, as long as it's a positive charge, it's going to be pushed away from our Q1. That makes sense? So if you have a little charge on a stick, okay, they sell them at the fair, charge on a stick, and you move them around, okay, and it's going to push your charge away from this particular place. Yeah? You guys follow me here? Okay. So Q1 is going to have an electric field. So what we're drawing here, we are drawing another electric field around this, okay, around this positive charge. Okay, and so here's the idea for when we're drawing an electric charge, drawing an electric field. These arrows are the direction that the particle would travel if the particle is positive and you were to let it go in the field. So wherever you are in the field, okay, what would be the force on that charge in the electric field? Well, and by default, that is called a test charge. The test charge is always positive, right? So if we drop a test charge in here, it is going to travel radially away from this particular discharged particle. Yeah? Okay, so what would this field like? Okay, so this is a positive field. All right. What would this field look like if Q, that's what we're going to call this Q1, if Q1, what if Q1 were negative? What would the field look like? Yeah, all of the arrows would now be pointing toward Q1, right? So here's Q1, or so all these are going to get to Q1, okay, if this were negative, because if we move a positive charge towards Q1, it's going to be attractive rather than repulsive. These arrows are the direction that a positive test charge would move if we have a negative field. If we were to have, and we're going to separate here, so we're going to have gravitational field, and then we're going to have an E field. If we have two gravitational objects, and you bring a third one into play, it is the three-body problem. What do you think the direction of motion of this particle would be? This is the three massive particles, right? So this is going to experience a field in that direction, and it's going to experience a lesser pull in that direction, right? So from this point, what do you think would be the direction of the acceleration on this object right here? If these two masses are the same, by the way, two equally massive planets, and you have an asteroid that's coming into proximity of both of them, right? Well, but wouldn't this have something to do with it? Yeah, it's going to be kind of weird. It's actually going to look something like, let's see if I'll draw it in, draw in purple here. No, that's not. It's going to be the sum of the vectors. Right? Can you guys see the pink in there? Okay. Right. So, what would happen to this object if it was right here? What's that? Yeah, it's supposed to be dead center in between them. What would the force diagram look like? What would the free body diagram look like on this? Well, this mass is going to pull it in what direction? Right? And this mass is going to pull it in that direction. And if both masses are the same, and it's the same distance from both of them, what is the net force on this object? 0. Yeah. Okay, now, stepping aside, this is actually called a Lagrangian point. Okay, this is a point where the potential energy actually is a 0, is a minimum. Okay, and if it were to move anywhere other than this exact spot, okay, it would start accelerating away from this spot. So it tries to maintain its position right there as much as possible. And any deviation from it starts to accelerate it away. Okay, but the point is, would this have a field line? Would there be any field line right here in the middle? What would the direction of the acceleration of this object be? It's 0, right? If there's no force, then there's no acceleration. So there would not be a field line here. But if we move away, okay, then we're looking at field lines that are attracting it. So if we have a couple of objects, and I'm going to need you guys to work with me here. There is a dotted line right down the middle of these guys that any object that sits on this line is going to accelerate towards. Okay, so does this make sense, what I'm drawing here? That if we're a little to one side or a little to the other, it's going to be attracted to one planet or the other. Yeah, but there's this equilibrium line in between the two, right? So our field lines are going to be okay. So does this make sense? What we did right here. We have a massive object that comes into this range. Okay, it's going to accelerate along these lines. It gives you an idea of how it's going to accelerate. Yeah. Okay, so now over here with an electric field, it's a little different because we can have different charges. Okay, if these are opposite charges, wouldn't they have, and we'll call this one plus, and this is negative over here, would they already be attracted to each other? So if you put a positive charge in the middle of them, wouldn't it experience that direction? If we put a positive charge, so it's going to repel from the positive and be attracted to the negative, it would go straight in between. Yeah. If we put it a little bit above, it's going to repel away, but it's going to be attracted toward that one, so it's going to have kind of an arc to it. Same thing below. And then, oh, and that's it for today. Okay, so continuing from last time, the field lines that we have, remember that along the field lines, these are the direction that an object will accelerate at any point in our space around our objects. So if these are two massive objects, then because gravity only works with massive objects and it's always attractive, okay, wherever we put a massive object around these guys, it's going to follow these lines that are coming in towards one of the massive objects. And if it's somewhere in between, it's going to be somewhat affected more than one than the other, and that's why we have these curves that are avoiding the center line, because if it's on the center line, then it experiences an equal force between both sides. We might accelerate straight down, but it would be equal to both of them, so it would just kind of travel along the middle. Right at that spot right there would essentially be a net force of 0, because if it's right in the middle of two equally massive objects, the force on that object would be equal in both directions, right? But if it moved off of that point, then all of a sudden you would have a differential force, and it would start tracking in towards one than the other. And so in fact, we could even do another one that's like in here. Okay, so that's for gravitational field lines. For electric field lines, we have the rules are a little different, but the idea of the line is the same. That if they represent what the direction of your acceleration, what it would be at any point around our electrically charged objects. Okay, so we have rules for these, and here they are. Rule number 1: the arrows are in the direction of acceleration at that point in space for whatever your massive object is, or whatever your positive test charge. Right, so green is for our electrical ones. So, okay, so a mass, because all mass is attractive, it doesn't matter if it's positive or negative. You can't have negative mass, and so they always attract each other. But for electric charges, because you can have positive and negative charges, we assume that you are testing a field, you are placing a positive charge into an electric field. And so the field lines are the direction of the force on that charge at any particular point. Follow me there? Okay. Okay, 2, the lines never overlap or cross. And logically, that should make sense, because if they were to cross, then that means there would be two different directions that your object would be flowing, that would be traveling at that point, and that doesn't work. 3G for gravity. Okay, the lines are always toward a massive object. Okay, towards your planet or star, whatever gravitational field you're in. And 3E, they are always away from positive and towards negative, because that would be the direction of a positive charge. A positive charge will always be pushed away from a positive charge and always be attracted to a negative charge. So that's why over here we have arrows going from the positive to the negative. Okay, in our electric field. Okay, and then you're going to have an assignment that is going to practice those. So we will stop that lecture there.